Alright, in this last video in section 13.6, I'm going to look at question number 7, which says that the temperature at the point xyz is given by the function t of xyz, which is 200 times e to the minus x squared minus 3y squared minus 9z squared. Temperature is measured in degrees Celsius and distances are measured in meters. So for part A, we're asked to find the rate of change of temperature at the point P with coordinates 2, -1, 2, in the direction directly towards the point Q with coordinates 3, -3, 3. Okay, so up here I have a picture of our point P, and imagine we're standing here at P, and then we're going to start heading in this direction directly towards this point Q. And what we want to know is, right, how fast is our temperature changing as we move in this direction? All right, so now the first thing to point out here is that this vector PQ, our direction of motion, has components that can be found by subtracting the coordinates of our points P and Q. So in other words, 3 minus 2 would be 1 for the I component of the vector PQ. -3 minus a -1, that'd be -2 for the J component, and then 3 minus 2 would be 1 for the K component. Okay, now notice this direction vector is not a unit vector. Its magnitude is the square root of 1 squared plus -2 squared plus 1 squared, and that is the square root of 6. So what do? Well, we're going to go ahead and consider this vector u that has unit length and has the same direction as our vector PQ. And we can find that vector by just dividing PQ by its magnitude. So this would have components 1 over root 6 minus 2 over root 6 and 1 over root 6. Okay, great. So now to go ahead and find our directional derivative, the first thing we're going to need is our gradient. So let's go ahead and compute the gradient of our temperature function. Do that up here. So we need to compute these partial derivatives. All right, and now for the x derivative, well, I'm going to have to apply the chain rule and differentiate what's up in the exponent position with respect to x. And that's going to give us a -2x. And that will multiply the 200. And so I'm going to get -400x times our exponential term. And this exponential is a messy expression, and it's going to come up here a couple times. So for the moment, I'm just going to say e to the box there, where this box is standing in for this messy exponent expression. Okay, so then for the y derivative, what will we get? Well, a -6y from the chain rule factor, that'll multiply the 200, so that'd be a -1200y times our exponential expression. And then for the z derivative, I'd get -18z, so that'd be multiplying the 200 to give us -3600z times our exponential expression. Okay, now I'm going to go ahead and factor out what's common in each component, and that would be -400 and the exponential. And here now I will go ahead and write the exponential expression in full, so minus x squared minus 3y squared minus 9z squared. And then we have what's left over, and that would be x, then 3y, and then 9z. Okay, great. So now let's go ahead and evaluate this gradient at the point where we're located, which is P, right? And its coordinates are 2, -1, 2. So if I plug in 2 for x, -1 for y, and 2 for z, you can check that the exponential term will be e to the minus 43, so that's a really small value. And then the vector here would be 2, -3, and 18. Okay, so this right here, I'll go ahead and just put this in a box just for our reference. We are going to need this, of course, very important. So to now go ahead and compute the directional derivative, so we can now say the directional derivative of our temperature function at the point P in the direction of this unit vector u will be this gradient vector of t evaluated at 2, -1, 2, dotted with this unit vector u. So put another way, right, I'm going to get this thing right here, the gradient, so minus 400 e to the minus 43 times the vector 2, -3, 18. And then I'm dotting that with our unit vector, which has components 1 over root 6, -2 over root 6, and 1 over root 6. Okay, whew, it's pretty involved. All right, now I'm just going to leave this minus 400 e to the minus 43 out front for the moment. So let's see now what we're going to get for the dot product result, right? I'm going to get 2 over root 6, then a positive 6 over root 6, and then finally an 18 over a root 6. Now altogether that's what, 26 over root 6, and if you multiply that by this minus 400 e to the minus 43, you get a whopping minus 10,400 e to the minus 43rd power divided by the square root of 6. Okay, now I'll go ahead and include units in my answer, right? This is a rate of change of temperature with respect to distance as we move in the direction U. So this would have units of degrees Celsius per meter. Okay, so this right here is our answer. But to give you a feel, how big is this? It's really small. If you use a calculator, that exponential term is so extremely small. It's about minus 8.98 times 10 to the negative 16th power degrees Celsius per meter. Okay, so the sort of the big takeaway here is that our temperature would be decreasing. Sorry here, I'll try that again. Get everything in the answer box there, but it will be decreasing, but at a rather small rate. Okay, so that is part A. Whew, that was a lot. How about, but there's some, one other thing, right? There's some really useful computational things to keep in mind here. This factoring out really is a lifesaver. If we didn't do that, this would actually be far messier. So that's one really big takeaway from this problem, as messy as it is. Okay, so now let's go ahead and check out B. This is asking us, right, in which direction does the temperature increase the fastest at the point P? Find this maximum rate of change. Okay, so here we are at P, and now instead of moving in this direction directly towards this point Q, right, we want to choose a direction. So we're going to choose some direction to move in, right, such that the rate of change of our temperature is as large as possible. And what do we know about maximum rates of change? Well, we know that we should head in the direction of the gradient. Okay, so the direction of max increase is simply the gradient of our temperature function evaluated at the point 2, -1, 2. Okay? And we already know what that is, right? That was just the vector minus 400 e to the minus 43rd power times this vector. It was 2 minus 3, 18. Okay, so this would be our direction to max increase. And then what was the max rate of change again? Oh, that was the magnitude of the gradient. So the max here of our directional derivative of our temperature function at the point 2, -1, 2 in this direction here, which will be the direction of the gradient. This is just the magnitude of our gradient evaluated at our point. So here I'm going to take the magnitude of this thing, which is minus 400 e to the minus 43rd power times the vector 2, -3, 18. All right, now notice the minus 400 and the e to the minus 43, that's just a scalar value. Okay, so this is going to come out front, so to speak, except it also, since it's a magnitude, it's going to change the sign here on the 400. So we're going to get 400 times e to the minus 43rd power times the magnitude of this vector 2, -3, 18. Okay, and now the magnitude of this vector right here happens to be, just to spare you the calculation, it's the square root of 337. So we're going to get 400 e to the minus 43rd power times the square root of 337. And the units there again would be degrees Celsius per meter. And because of this exponential term, this is also really, really small. It's a little bit bigger than our answer to part A. Remember, this is the largest that our rate of change could be as we move from the point P, but it's still pretty darn small. It's 1.55 approximately times 10 to the minus 15th power, and this is degrees Celsius per meter. Okay, so yeah, still very small, but larger than what we saw for our answer to part A. And that's going to do it for this problem and for section 13.6. I'll see you next time.